routine contact tracking across a calm ocean. Then, the AI's certainty fractures. Years of Chinese investment in warship automation promised perfect targeting, faster than humans could think. Yet when a supposedly robust kill chain met a 50-year-old US deception tactic, everything destabilized. Weapons locked onto ghosts. After decades of digital arms races, belief itself became the weapon. And in that instant, the math that underpinned modern warfare collapsed. How does a legacy trick unravel the foundation of autonomous battle? Speed became the doctrine. In recent years, Chinese naval planners pushed for automation that could compress the decision cycle to seconds, not minutes. The Type 055 destroyer, equipped with networked sensors and AI-driven command, was introduced as a solution to human bottlenecks in targeting. In a 2026 simulation, one Type 055, supported by 2 unmanned motherships and dozens of drones, coordinated fire and maneuver against a US destroyer group. The entire engagement, from initial detection to weapons release, unfolded in less than half the time it would have taken a human team. Algorithms processed sensor feeds, classified contacts, and assigned weapons with a consistency planners described as mathematical. Fusion architecture engineers described the goal as eliminating ambiguity, building a system where every contact could be identified and acted upon before an adversary could react. The belief was simple. The faster the machine, the smaller the window for error or enemy interference. That belief shaped procurement, training, and the entire architecture of China's new warship fleet. In practice, the difference was stark. Human operators, even under ideal conditions, needed tens of seconds to verify a radar track, cross-check with other sensors, and authorize engagement. AI-driven systems did the same in milliseconds, feeding a sense of inevitability into the operational rhythm. The assumption was that speed would guarantee certainty, that compressing the timeline would make deception or confusion impossible. The system was designed to trust its own speed. The question was whether that trust could be broken. A modern naval kill chain begins with intelligence, surveillance, and reconnaissance, collecting raw data from radar, sonar, electro-optical, and electronic signals. Each sensor delivers a stream of measurements: bearing, speed, emission type, and course. These inputs arrive asynchronously, sometimes conflicting, often incomplete. The system's first task is data association, matching fresh reports to existing tracks or starting new ones when patterns diverge. Sensor fusion algorithms then merge these inputs, weighing each by source reliability and historical accuracy. The result is a composite track, scored by confidence. This score is not a guess. It is a calculated probability, updated with every new report. Tracks with low confidence are gated out, removed from the display, and excluded from further analysis. The gating threshold, set by system doctrine, acts as a filter. Only tracks that meet the statistical bar for consistency and plausibility survive. Once a track passes the confidence gate, classification routines assign identity, warship, merchant, drone, or decoy, based on signature libraries and movement profiles. The system then cues targets for engagement, prioritizing those that fit threat models and operational rules. Weapons assignment is not random. It is the final node in a chain where each link, sensor, fusion, confidence, and classification must hold. The process is continuous, running in milliseconds, with each node feeding the next. The weapon, in this architecture, is not just the missile or torpedo. It is the certainty that the system has about what it sees. The entire engagement depends on this chain. Break one link, and the outcome changes. A shaped input arrives. On the fusion display, a new contact appears. bearing, speed, and course all fall within expected parameters. The system's algorithms begin to process the stream, comparing it against stored movement profiles and signature libraries. There is no noise, no conflicting data. Confidence in the track rises sharply. Within seconds, the false contact is promoted from a low-priority blip to a high-confidence target. The gating logic, tuned to filter out ambiguity, does its job. It removes any outliers and leaves only the clean, algorithmically consistent track. This is not a brute force attack. The adversary has studied the system's thresholds, crafting a decoy that mimics the kinematics and emissions of a legitimate threat. A low-cost unmanned surface vehicle equipped with a tuned radar reflector and software-defined radio broadcasts a signature that matches the AI expectations. The fusion engine, designed to reward consistency, accepts the input. Operators see a stable, reliable track. The system's own metrics confirm it, and confidence exceeds the engagement threshold. Adversarial machine learning research has shown how small, intentional changes can fool neural networks into high-confidence errors. In this scenario, the same principle applies. A minor perturbation, just a few degrees of course, a slight adjustment in speed, creates a track that the system prefers over noisier, real-world data. As one machine learning specialist described it, the vulnerability is not in the sensors, but in the trust the algorithm places in patterns that look perfect. The system is not being blinded, it is being guided. The false track is now ready for weapons assignment. Track confidence passes the threshold. In milliseconds, the fusion engine prunes away any inconsistent data, leaving a single, high-certainty contact on the display. The interface updates. Low-confidence tracks vanish. Operators see only what the system has accepted as truth. Behind the scenes, sensor resources, radar beams, electro-optical cameras, sonar arrays are automatically retasked to focus on the promoted track. The system collects more measurements, each reinforcing the original error. The confirmation loop tightens. Every new data point fits the expected pattern because the sensors are now looking only at the decoy. Confidence in the false track keeps rising. At this stage, the weapons assignment queue locks. Fire control systems pre-stage missiles or torpedoes against the target. The interface prompts the operator. Target locked, ready for engagement. The override window narrows to seconds. Doctrine and design both reward rapid action. Operators, trained to trust the fused picture, face institutional pressure to commit. The system presents a single, internally consistent truth. Hesitation means risking the ship. In the compressed timeline of automated combat, there is no practical space for doubt. The decision is now kinetic. Once the queue locks, the ship is committed. Resources, attention, and weapons are tied to a target that never existed. The process is invisible, silent, and once started, almost impossible to reverse. A single false target draws more than attention. It draws resources. In the Type 055 simulation, 2 to 4 anti-ship missiles can be expended on a decoy before operators recognize the error. Each missile costs millions and cannot be replaced at sea. Recovery from a false engagement triggers a full sensor reset, leaving the ship blind for up to 15 minutes. During this window, the vessel is exposed and unable to respond to real threats. Maneuvering to regain situational awareness burns additional fuel, sometimes increasing consumption by 10 to 20% per engagement. Drone sorties tasked to investigate or strike false contacts return with depleted batteries, reducing available coverage for hours. Across a task force, these effects compound. Munition stocks dwindle, fuel reserves tighten, and operational tempo slows. The cost is measured not just in lost weapons, but in readiness and the ability to sustain action as the engagement drags on. In 1976, U.S. Air Force deception doctrine distilled the method to a single line. The success of deception rests on its credibility, which demands consistency between feints and the enemy's anticipated actions. The principle was not to hide. It was to present a pattern so believable that an adversary would accept it as truth. In the age of AI-driven kill chains, that doctrine finds new relevance. Algorithms designed to reward consistency inherit the same vulnerability. When a false contact is shaped to fit a system's expectations, the network commits resources, attention, and weapons based on a credible illusion. The doctrine's edge is not technological. It is psychological, embedded in the architecture of belief. Deception now operates at machine speed, but the foundation remains unchanged. Credibility through consistency. Whoever shapes the pattern that the system trusts controls the outcome. In the end, it is not the hardware, but the belief inside the network that decides the fight. Today's battles are shaped less by firepower than by the certainty behind each decision. As advanced navies automate, the ability to manipulate belief inside the network becomes decisive. In the end, it is not the smartest system that wins. It is the one least certain it cannot be fooled.